This is a video to explain Chapter 2, Section 2, which deals mainly with what we call the normal distribution, but density curves in general. So that is the big goal, or at least most of it. There's part of it this is gonna be the part 1, and then there's gonna be a shorter video. This is the part 2 of this section that deals with assessing normality. So like I said, the curve that we're going to be dealing with, the main density curve as we call it, it's going to be a normal curve. Later in the year we'll deal with uniform curves, which just go straight across. But what is a density curve? A density curve is basically a graph that we use to solve problems, and there's two main features of it. And number one is we're going to scale it such that the area under it, or the area between it and the x-axis, actually, the area under it is always equal to exactly 1. That makes our calculations a little bit easier in that regard. And the second property of a density curve is that it's always, like I just alluded to, it's always above or on the x-axis. It never goes below the x-axis, always above or on the x-axis. And we use density curves to tell us, we calculate probabilities, and we also can calculate percentiles and related things. And so our most popular one is going to be a symmetrical one that we call the normal curve. And the reason we call it the normal curve is it occurs a lot. It occurs sort of normally, and it's kind of mound-shaped and symmetrical like that. We also, and we talked about this in previous videos, we can encounter something that is, let's say, skewed to the right. And so let's say, for instance, a lot of money distributions would be skewed to the right. Like, let's say if we were looking at the salaries that the workers in this city earn, and you've got a lot that earn relatively not that much, which is sort of the middle class, but we have a few that earn a heck of a lot. You know, maybe the CEOs or the managers are over here. And so what we're going to use density curves to do is we'll find areas. And so let's say here's the mode of this thing, the number that occurs most often. And so let's just pretend that that's like $50,000. And then the median, let's say it's going to be in here. You remember from previous videos, the median is the number to where 50% of the values are below it and 50% are above it, roughly. It's the 50-50 line. Then we're going to have, and so the median is in essence the number in the middle. Then we're going to have the mean. The mean is what you think of as the average. It's just the total divided by the number of numbers. And in a right-skewed distribution, we talked about this before. In a right-skewed distribution, this is an important thing about density curves, the mean is going to get pulled toward the skewness. And so in a right-skewed distribution, the mean is going to be bigger than the median. The mean is actually at the balance point, is if this was made of solid material. Okay, and so these large salaries are going to pull the mean over here, and so it would be in essence the balance point, or if you think of physics like the fulcrum of the physics. And what we're going to do is we're going to say we'll be asked, you know, what's the probability that if you randomly select one of these people that lives in this place, what's the probability they make more than, let's say, $70,000? And what we'll do is we'll say, well, $70,000 is like right here, and we'll use we'll use more than 70,000 to be greater than, like that. And so we'll use, in essence, the methods we're going to talk about to find this area. Now, in this particular curve, we won't, but we will with a normal curve. So that is what we'll do. Or the other thing is we could, well, what's the 30th percentile, let's say? Well, the 30th percentile, let's say, is over here, and we'll use our methods. So this would be 30%. And so what is this number right here? We'll talk about methods we're going to use to find that today in a normal curve. Or let's say if we have a density curve that is a left skew to it. As a left skew to it. So let's say it looks like that. Let's say these represent, every point under here represents the score on an easy test. Most people scored really well, but there's a few people that didn't score too well. All right. So in this case, once again, the median. So the median is the number in the middle. It's got 50% to the left, and it's got 50% to the right. The mean gets pulled toward the tail, toward the skewness. So here's the mean, and here's the median. So that is a popular thing that happens. And so what we'll do, it should say, what's the probability of getting someone that made less than, let's say, 72 or whatever. And so we would find that area. And that area would represent the probability. It would be this probability over, or this area over the area of the whole thing, but the area of the whole thing is 1. And so that is in essence what a density curve is. But the main deal in this section deals with this, what we call a normal curve. All right, a normal curve. And so the rest of this section, the main part of this section, is going to be finding values with this normal model, or this, what we call the normal model, the normal curve. The first thing is this in regards to the normal curve is what we call the 68, 95, 99.7 rule. We used to call this an empirical rule, and it's an important rule for you to know. All right, and it is this: in any normal curve or any normal model, 68% of the values are within 1 standard deviation of the mean. Of the mean. 95% of the values are within 2 standard deviations of the mean, and 99.7% of the values are within 3 standard deviations of the mean. So basically almost the whole curve is within 3 standard deviations. So in a normal model, so what that in essence will look like, and so let's say our normal model, it typically looks like this. Typically looks like that. Sometimes normal models can actually be taller than this or shorter than this, but just depending on what your standard deviation is. But so 1 standard deviation, so here's the mean. We typically call that mu or x bar. 1 standard deviation to the right is going to be halfway down this hill at this inflection point. In other words, the concavity of the graph here is going to change from concave down to concave up, if you've had that in another math class. And so we would say plus 1 sigma, and that would go to there. In 1 standard deviation left, minus 1 sigma, so that would go to halfway down this hill at this inflection point to right there. And so the empirical rule says 68% of this whole curve is within 1 standard deviation. Then if you go out 2 standard deviations to about right there and about right there, so this would be, minus 2 sigma, and this would be plus 2 sigma, 95% of the values are going to be within 2 standard deviations. So this only applies in essence to what we call a normal model. And then lastly, if we go out 3 standard deviations, we've encompassed just about everything. All right, it's 99.7% of the curve. So whenever you, in essence, have a normal model, when you say something's very normally, it is extremely rare to get something that's 3 standard deviations below the mean or 3 standard deviations above the mean or more unusual. It happens well less than 1% of the time. And so, and that's something that's going to be an important fact for us. When someone claims, oh, there's something that's very normally, let's say the weights of these animals or whatever, they're very normally with a mean of, let's say 40 pounds, let's say our mu is 40, and let's say our standard deviation is equal to 10. So that means, 51 standard deviation of the mean, that wouldn't be that unusual. 2 standard deviations above the mean, 60, that's starting to get out there. But it would be really unusual to encounter one of these animals that's weighing 70 or that's weighing 10, 3 standard deviations below the mean. That would be really unusual. And so that is in essence the 68, 90, 95, 99.7 rule. So anyway, so let's look at a context, and hopefully in these problems this will start to make sense. All right, the times of phone calls to a service to the customer service department of a company follow an approximately normal distribution, so right there, with a mean of 7 and a standard deviation of 1.5. All right, so use the 68, 95, 99.7 rule to find the percent of calls that are more than 8.5. And let me say this in regards to a normal model. It's really impossible for something, any finite distribution, to vary exactly normally. So we really shouldn't say at any time that any finite or real world situation where something varies exactly normally, because there's an infinite number of points in here. And this is a very specific curve. So in essence, whenever we want to describe something very normally, we really should say it's very approximately normally. So anyway, so use the 68, 95, 99.7 rule to find the percent of calls that are more than 8.5 minutes. So what I'm going to do is I'm going to, in essence, draw this curve. All right, so let's draw this curve. And so we've got this normal, when you draw a normal curve, so it looks something like that, all right? So we'll label this as normal, all right? And so the mean is right in the middle. So the mean in this case is 7, so we say 7. If I go up 1 standard deviation, that is over to here. If I go over to where halfway down this hill, right at that inflection point, so 1 standard deviation is 1.5. So that would be at 8.5. And if I go down 1 standard deviation, that'd be halfway down this hill at this inflection point, so that would be 5.5. So I know right now that 68% of the values, in this case the times that it of the phone calls, are between 5.5 and 8.5. So what I'm going to do to solve these problems is I'm going to find the area of each of these sectors in it so I can answer various questions about it. So if 68% is from here to here, and this curve is perfectly symmetrical, so that means if I divide that by 2, 34% is between 5.5 and 7, and 34% is between 7 and 8.5. Then if I go out 2 standard deviations, that's going to be about here, so minus 1.5, that would be to 4. So that would be 2 standard deviations below the mean. 2 standard deviations above the mean, so that is going to be 10. So that'd be 2 standard deviations above the mean. So how far out have I gone? Well, according to the 68, 95, 99.7 rule, the area of these two things is going to be, well, it's going to be 95 minus 68. 95 minus 68, and that, in fact, is 27. And if I divide that by 2, that means each of these areas is 13.5%. 13.5%, like that. Okay? And then if I go out 3 standard deviations, I'd subtract 1.5 there, and so that would be 2.5. If I go up 1.5 there, so that would be 11.5. All right, that would encompass 99.7%. So 99.7% of the curves between there and there. And if I say 99.7 minus 95, so that means 4.7% are going to be here. And if I divide those by 2, so that ends up being 2.35%. That would be 2.35% are between each of those. And then lastly, I know 0.03 is on the outside. And if I divide that by 2, so that's going to be, and so that's going to be 0.15% that is beyond that. In other words, you know, a very small percent of the curve is outside of that. And so now, okay, what percent of the calls are more than 8.5? And I can just add those up. So if I go, so the answer number 1, if I say, 13.5 plus 2.35 plus 0.15, and so that ends up being 16%. So this is 16%. Or you could just realize that half of the curve is 50%, and you could subtract off that 34%. So 16% of the curves is above 8.5. And so then the next question is, all right, what percent of the peaches, or it should be peaches, what are the peaches calls? I changed the problem here. What percent of the calls are, what percent of, I made up a different problem for another worksheet and left it in there. But anyway, what percent of the calls are between 4 and 11.5 minutes? Well, that would be between here, that'd be between there and 11.5. And when you add up all of those percents, that ends up being 97.35%. Now, we're also going to have a calculator function that is going to solve these sorts of problems, but understanding the 68, 95, 99.7 rule is the first major concept really in this to be able to do these problems. Now, before I get into the major normal curve problems and calculations, there's really 3 things that you're supposed to do to officially show your work for normal curves. And believe it or not, it's a bit of a controversial area what you need to do to show your work. 3 things that you need to do to draw the normal curve with the proper shading, and I'll show you what I mean by that. To find the z-score, which we talked about that previously, but we'll do it again. And then lastly, to find the answer to the problem. If you show those things, that's considered properly showing your work. And we're also going to talk about, calculator syntax, which many of the stats gurus don't like, but you certainly can get full credit on the AP Stats exam if you do what I'm fixing to say. So let's get into the main part of the deal, and that is solving these normal curve problems. Okay, so the scores in a test vary approximately normally. Okay, so that's telling me, hey, this is a Chapter 2 problem. Approximately normal with a mean of 81.4 and a standard deviation of 3.6. If you randomly select one of the scores, finds the probability it'll be less than 76. All right, so what we've got here to draw this curve, our situation here. So this curve, anytime you draw a curve, always label it as normal. We're going to have, some other curves that sort of look similar to this. So make sure you always label what your curve is. Then always label the mean. So this would be 81.4. And then one standard deviation, I'll just say, well, sigma is equal to 3.6. And so if I go up one standard deviation to there, 3.6, so that would be 85, I believe, and down one standard deviation, so that would be 81.4 minus 3.6, and so that's equal to 77.8. That just sort of gives me a reference as far as how unusual values are. And what the heck, I'll go up one more standard deviation, 2 standard deviations about there, so that would be 88.6. And if I subtract, that'd be 74.2. So that would be 2 standard deviations above and below the mean. And that allows me to see the curve and to see what unusual values are. Every point under here, in essence, represents a test score. It represents a person and their test score. So the question is, if I were to randomly select a point under this curve, if I were to randomly select one of these people, what's the probability? It's going to be less than 76. And so what I'll do, to show the proper shading, what I'll do is I'll guess as best I can. 76 is going to be somewhere in there. So I go, there's 76. And it says less than 76. So I want to find this area that is in essence less than 76. And so what we're going to do is we're going to find, there's a couple different ways we're going to be able to find this area. We are going to, we're going to be able to use a function on our calculator, but we're also going to use some tables. And that, yes, you do need to know how to do this. So the first thing we're going to do to find this area is we're going to find the z-score for our value. So the z-score is the number of standard deviations that this value is above or below the mean. So it's below the mean here, so our z-score will be negative. And so that's going to be 76 minus 81.4 over 3.6. That's our z-score formula, the x value minus the mu over sigma. And you have to memorize that. But it's just the number of standard deviations my value is from the mean. And so in this case, it ends up being negative 1.5. So my value is minus 1.5 standard deviations below the mean. It's not way below the mean, but it's pretty significantly below the mean. So to find this area here, we're going to go to our table A. And actually, if you didn't have access to table A, you could Google normal calculation tables. And you'll be given this on the AP Stats exam. You'll be given these formulas, and you'll also always have access to tables like these on the test. But it's Table A, standard normal calculations. And so you'll notice on the left side it has z-score going down this left column, and then up top it has notice it has the tens place and the ones place, and on the top it has the hundredths place, or it has the ones place and the tenths place. And then it's got the hundredths place there. So we're looking for negative 1.50. And what this table, these values in the table, notice the graph up here, it's telling us this area that's to the left. That is in essence a probability. It's the probability, if I were to randomly select one of these points here, what's the probability that I would get a value less than my z-score? All right, so my z-score is negative 1.5, so I go to negative 1.5. Then the hundredths place is 0, it's negative 1.50, so it's there. So there's my answer, 0.0668. And so that is it. And so my area is equal to 0.0668, and that is my answer. And I've drawn the curve and I've shown the z-score, and that's showing my work. And so that problem is sort of the heart of the problem in this chapter. Now, let me show you how to use your calculator to do that, and which is probably what you're going to do most of the time. We're going to use a function called normal CDF. All right, and so if I take my T84 And we're working with the distribution here, and the distribution menu is right above the vars button right there. So that's what we're going to be using. So if I go second vars, and I go to normal CDF, we're never going to use normal PDF. Never use normal PDF. In this chapter, we're using normal CDF and inverse norm. Those are the two big functions of this chapter. So I go to normal CDF. All right, it might take you to this screen and it might not. Most of the newer ones do. And so what I'm going to enter in is I'm going to enter in the left value, the lower value of my shaded area. Well, the shaded area is negative infinity, which that's what my calculator has in there automatically. Anyway, but if it didn't have that, you could just hit like negative and hit like negative 9 billion or whatever, realizing there's almost no area, anything below like 70 here. So like negative 900,000 is going to have like nothing. The upper part of my area, in this case, is 76. So I go 76. All right. And then now with my z-score of negative 1.5, what I've done is that is a standardized value. And I could just use, well, let me come back to that. Well, anyway, so my mean is 81.4, and then my standard deviation is 3.6, like that, and then that will there, and there it goes, and there's my answer right there. And so that's using normal CDF. Now, in many calculators, what it's going to do, it's going to automatically take you, and let me just kind of delete a bunch of values here. In some of the older 83s and 84s, what it's going to do is it's going to automatically take you to this screen. It'll automatically, when you hit normal CDF, it'll automatically just take you to that screen, right, like that. And so what you're going to enter in is the lower bound, and the negative, make sure and hit the negative button, not the minus sign. Hit the negative button. So you just go 9 minus a really small number, which is that, and then comma, and then the comma button is right above the 7 button right there. So you hit comma, and then my upper bound is 76, and then you hit comma, and then my mean is 81.4, and then comma, my standard deviation is 3.6, and then you got your answer. So there you go. All right, what about now, having said all of that, what about the probability of more than 83? Well, 83 is somewhere up here. And I'm not going to, like on a test, I wouldn't ask you to draw a ton of curves or whatever. So you can just draw it on this same curve. So 83, that's going to be about right here. So there's my value. There's 83. And it wants more than 83. If I were to randomly select one of these scores, which probably is more than 83. So this would be my shaded area. So what we could do is we could find the z-score. So the z-score is 83 minus 81.4 and 3.6. And that, in fact, is going to equal to 0.4 repeating. And so let's find this area that's greater than. Now, realizing this is that on this table, it always finds the area that's below it. So when we have an area that's greater than, what we'll do is we'll find the area that's below it and subtract it from 1, because this is a density curve, the area under it is 1. So we're looking for a z-score of positive 0.44. is what we're looking for. And so on this sheet, all the z-scores are negative. So I go to the next sheet on my table packet, and I notice the z's are positive. So I go to z.4, and I go over to the 0.04 column. And of course, it's going to, so, and it's 0.4 repeating, so it's going to be somewhere between that value and 0.045. So if you wanted to prorate it and average it, that'd be fine. But this is close enough. It's 0.67. But you would realize that's the area that's below my value. I want the area that's greater than that. So it's 1 minus 0.67. So this is going to be 1 minus 0.67, and so that is going to be equal to approximately 0.33. So about a third of the curve is in essence above that. That's one way of doing it, you have to understand. The other way is normal CDF. So we'll go normal CDF, and we'll go from 83 to infinity. That's the little symbol for infinity. And our mean is 81.4, and our standard deviation is 3.6. Whenever you draw this, to get credit for showing your work, by the way, you have to label these values. So you have to label these values. That is LB for lower bound. That is UB for upper bound. That's my mean. That's my standard deviation, mu and sigma. Okay, like that. And so let's see what happens when we do that. And so I will go second distribution, normal CDF, hit enter, and I'm going in this case from 83 to infinity. So I go 83, and you can just hit like 9 trillion. That's, you know, effectively infinity on this scale. Same mean, same standard deviation, and there we go. It's 0.32836. That's a more of an exact value, 0.32836. So there we go. Now, what about in between? So in between, so if I do my little curve here, draw a little rough sketch. Here's 81.4 and the standard deviation above it, and so that's going to be 85. Standard deviation below it, that's 77.8. I want what percent of this curve between 75 and 84? Between 75 and 84. I want the area there. So the area of that curve, and so what we'll do is what you could do is find the z-score for each of those. All right, go to the curve and subtract the areas that you get, and that would work. But certainly the quicker way, I'll just do normal CDF. So I go second distribution, normal CDF, and I go, my lower value is 75, my upper value is 84, mean of 81.4, standard deviation of 3.6, and I get 0.7272. So that would be approximately equal to 0.7272. To officially show my work on that, I have to write the word normal CDF. 75 lower bound, 84 upper bound. The mu is 81.4, and then the standard deviation is 3.6, and so that is mu, that is sigma. So officially, I would get a credit for this because I've said what the curve is, normal, and I've labeled my parameters. I've labeled my numbers here, lower bound, upper bound, mean, standard deviation, and then I have the proper answer. And so that would, in essence, give me credit for that. All right, then the next sort of problem is, in essence, inverse norm problems. What is the 70th percentile of the scores? So 70th percentile means this, as we discussed in a previous video. 70 percentile means 70% of the values are below this value. So the 50th percentile, which is the median, which is the same as the mean here because we have a symmetrical distribution. So this is 81.4. Once again, right up and below one standard deviation, so that's 85, and so that's so that is so that's 77.8. 70th percentile is, it's going to be somewhere around here. All right, it just means 70% is to the left of it. Okay. All right, and so what I'll do, and we've got, this is in essence an inverse norm problem, but what the heck, I'll use my tables first. So what we would realize is this, on this table here, these values are in essence percentiles down here. And so I'll find as close as I can to 70%. So as close as I can to 70%. So there's 69.85% and there's 70.19%. So it's somewhere around 0.52 something. And I'll go with roughly halfway in between there. So I'll go 0.525. So that is the z-score of the 70th percentile, roughly 0.525. So my z-score is going to be 0.525, and I used the formula for z-score, and it'd be x minus my mean, which is 81.4, over the standard deviation of 3.6, and let's see what we get. I'll solve this for x, and so I will go 0.525, and then times 3.6 is equal to, and then plus 81.4, and so I get 83.29. 83.29. So that is in essence my answer. But the quickest way to do this is working with inverse norm. You use inverse norm when you're given an area and asked to find an x value. Normal CDF is when you're given an x value and trying to find an area. So an inverse norm is on the distribution menu. So I'll go second distribution, inverse norm. Now the latest versions of the 84 are going to give you the option of doing a left area, a center area, or a right area. So I tend to always use the left area, and that's what some of the older versions of the 83 and 84 do. So my area to the left of my value is 70%. So I will enter in 0.7, not 70, and go like that. And then my mean is 81.4, and then my standard deviation is 3.6. Left area, and then I just hit paste. Older versions of the calculator will give you that option, and you just enter in those three numbers like that, and then hit enter, and it in fact is, so that's this, we got the same thing roughly, 83.19. So to show my work there, now like I said, you can, showing your work, you could be asked to draw the curve and show the relevant z-score in any normal curve problem. But the quickest way of showing your work in and that's the way we're encouraged to have you show the work, but the quickest way to get full credit in the exam is just to write inverse norm and then go 0.7, that's my area, and then mean of 81.4, standard deviation of 3.6. And so this is my left area, like that. And there's my mean mu and sigma, and then that would give us that answer. And so we would get credit for naming the distribution, labeling our parameters, and getting the proper answer. So that is the 70th percentile. If you get a 83.29 in this test, you are scoring better than 70% of people. All right, now, and then related problem sort of, what if the score is less than 80% of scores? So let's think about this. Well, less than 80% of scores means it's the 20th percentile. We got 80% is below it, 20% is below it. So we could just say inverse norm, 0.2, that is my left area. I'll label that as left area. And of course you could label it right area with 0.8 to be the same, but I tend to always work with percentiles. And the reason I do, like I said, the reason I tend to always work with left area, some of the older calculators only give you the option of left area. So anyway, and so here we go. So we'll do second distribution, inverse norm, 0.2, that mean that's standard deviation, and we go paste, and we get 78.37 approximately. So approximately 78.37, and so that is in essence the 20th percentile. And you sort of always want to look at these problems and see if they make intuitive sense. Like certainly on this one, you know, you're the 70th percentile, well the average, the mean, the median is 81.4. So you're expecting the 70th percentile to be kind of well above average, which it is. It's 83.29. And the 20th percentile, you're expecting it to be below average, which it is, 78.37. All right, then we have the concept of what is a standard normal curve. A standard normal curve, the thing to know about it, the mean is equal to 0, and the standard deviation is equal to 1. So when you hear the term standard normal curve, just realize what that means is in essence all of your values have been standardized. All of your values have in essence found, the z-score has been found. And so it's a mean of 0, standard deviation of 1. And that is in essence what on this table has happened. This is in essence a standard normal curve with a mean of 0 and a standard deviation of 1. And when you have a standardized curve like this, you can use z-scores in essence to find areas. So and then this is sort of a minor area in stats that isn't talked about much, but are deciles. And deciles, if you are, you know, if you know your Latin and if you know the metric system, a decile is in essence, you know, 10%. It is dividing the curve up into tenths. So in other words, the second decile is in essence the 25th percentile. So the second decile is 20th percentile, is equal to the 20th percentile. And so that is in essence, and that is what an actual, or the standard normal curve. So, all right, so the 20th percentile of the standard normal curve, so we will do this. And so we will go second distribution, and we'll do inverse norm, and 0.2, but mean of 0, standard deviation of 1, which after you turn your calculator off, it actually automatically defaults to that value. But so we enter, and so we get negative 0.8416. So it's approximately equal to negative 0.8416. And the 80th, and then the 8th decile, so the 8th decile is 8/10 of the way through the curve, in essence, it's equal to the 80th. It's equal to the 80th percentile. It is bigger than 80% of the values in the curve. And since it's perfectly symmetrical, you may be able to guess what it is, but let's see. Now, by the way, my calculator, if I do second entry, if I hit second, the entry function is right above the enter button. It'll enter in the last function just to give me a shortcut. And if I'll just go, I'll just arrow over here and change this to 0.8, and so that will tell me the 80th percentile, mean of 0, standard deviation of 1, left area. And so it's positive 0.8416. So it's positive 0.8416 because it is perfectly symmetrical. And so anyway, so that's the concept of deciles. And then lastly, we have some of the kind of more challenging problems that can happen to you in regards to normal curve problems that have occurred. These are, you know, the heart of this section is normal CDF and inverse norm and being able to, you know, to do those problems. But we also have some harder problems that tend to work with the formula for a z-score. Z-scores are really important concepts. So in this case, it says we have a drink machine that dispenses amounts of Mountain Dew in slightly varying amounts. The amounts vary approximately normally with a standard deviation of 0.18. The mean can be preset by the worker. What should the worker set the mean to if he wants a 16-ounce cup to be overfilled only 1% of the time? So what is happening here? We got this machine, and this curve represents the amount of Mountain Dew that is being dispensed. And we don't know what the mean is. That's what we've got to figure out. But every point on here represents the amount of Mountain Dew that is being spit out by this machine. But we do know this. At a certain point, it's going to overfill. It's going to put too much. Like over here, that it dispensed a lot of Mountain Dew. Over here, it dispensed not that much Mountain Dew, and most of the time, it's around this certain amount. But this represents when it goes beyond a certain limit, it's going to, in essence, overfill it. And it says we want to overfill it only 1% of the time. So overfills will only occur 1% of the time. And so, and at that point, that's where a 16-ounce cup is. So we want it to overfill a 16-ounce cup only 1% of the time. What would the mean have to be if the standard deviation is 0.18? So whenever you're asked a mean or a standard deviation or normal curve, you're going to use a z-score. And so remember, our z-score is our x value minus our mean divided by our standard deviation. How can we find the z-score, in essence, that is right here? And that is what we just did, inverse norm with the standard normal curve. The standard normal curve is a curve of z-scores. So what we will do is we'll find the z-score that goes, in essence, with 1%. And so we will say, okay, the z-score, so I get second distribution, inverse norm, and 99% of the curve is to the left of this. So I go 0.99, mean of 0, standard deviation 1, left area, like that. And so this is going to tell me the z-score that is at the 99th percentile. And so it is, in fact, 2.326. So 2.32635, giving myself plenty of significant digits. Now I can use I know what x and sigma are, but it asks me for what the mean is. So now I can use my formula. So this would be 16 minus mu over 0.18. And so I'll just use my algebra skills to find this out. And I've got that somewhat exact number in my calculator. So I'll just go times 0.18 is equal to, and then I'll subtract 16 minus 16. And so that gives me that. And then I just divide it by -1, and so it'd be 15.581. So I would say, well, the mean should be approximately equal to 15.58126. And, of course, always put your units in stats. This is ounces. So there we go. And that would, when you look at this, that sort of makes sense that if the average is 15.58 and the standard deviation is 0.18, 16, the 99th percentile is going to be way up there, and it is. And so there you go. That's one of the harder problems that can exist in a normal distribution problem. And here's another one. So this is, all right, in number 9, the mean of the drink was 15.8. So in this one, we set it to 15.8. Okay, so here we know that the center of this thing is normal. You get in the habit of always labeling your curves is what they are, which in this case is normal. So this is at 15.8. However, the standard deviation is no longer 0.18. what would the standard deviation need to be if you wanted the dispenser to overfill 16-ounce cups only 3% of the time? So that's a similar concept. Whenever you're asked to find what is the mean or standard deviation of this normal curve, you're going to use the z-score. X minus mu over sigma. And we want it to overfill only 3% of the time. So at 16, we want this to be just 3%. And so what we'll do is we'll do inverse norm. It is in essence 3% above it, 97% is below it. So we will do inverse norm of 97%. So I go inverse norm 0.97. Our mean, or mean of 0, standard deviation of 1, and that'll tell me the z-score for the 97th percentile. And so it, in fact, is 1.88079. So 1.88079 is equal to 16 is my x value, 15.8 is my mean, and then my standard deviation is what we're asked to find. So when I use my algebra skills in this regard, so 16 minus 15.8 is 0.2. So it's going to end up being 0.2 divided by the answer, which I can hit the answer by just do second and that button right there. And so it gives me 0.10634. So sigma is approximately equal to 0.10634. So there we go. And so that's how you would do that. And then lastly, so let's look at this guy. On the ACT scores of students at a large school district follow an approximate normal curve, mean of 18.5, standard deviation of 3.9. What are the outliers of this distribution? So what we've got here, and so this is sort of combining some concepts here. So the concept of an outlier that we did in chapter 1. So we've got this normal curve, and so this is normal. And so we've got, okay, the average right in the middle is 18.5, and the standard deviation, so plus 3.9, so that'd be 20.4. It'd be 21.4. And if I subtracted 3.9, so 18.5 minus 3.9, and so that's 14.6. And so that's just sort of labeling my curve. The question is, how far do I got to go out on this tail before it's an outlier? What's an outlier on the high end and on the low end? How far out do I have to go? And so remember our little formulas for outliers. So our little formulas for outliers are going to be this. It is anything greater than Q3 plus 1.5 times IQR. And the IQR is Q3 minus Q1. Or anything less than Q1 minus 1.5 times IQR. So we need to know what Q3 and Q1 are. So we'll figure out, so remember the IQR, the interquartile range, is equal to Q3 minus Q1. Remember, the Q3, what is it? It's the third quartile, the upper quartile. It is the 75th percentile. So to figure it out, what we'll do is we'll find the 75th percentile of this normal curve. And how do you do that? By using an inverse norm. 0.75, mean of 18.5, standard deviation of 3.9. So I label this as my left area, label this as mu, and this is sigma. And so then I would subtract the first quartile with the lower quartile, which is the 25th percentile, which is inverse norm of 0.25, mean of 18.5, standard deviation of 3.9. Hopefully I'm not being too messy here. So this is left area, this is mu, and this is sigma. So let's see what these things are. Let's see what these things are. So I'll use my calculator. And so, I'll go second distribution, inverse norm, 0.75. All right, my mean is 18.5, and my standard deviation is 3.9. So, and it's the left area. So that would tell me it would be 21. So that would be 21.1305. Okay, that is my Q3. Third quartile. Then to find, if I do second entry and do the same thing as 0.25, so 0.25 like that, that tells me my first quartile, my lower quartile, which is 15.8695. And so that would be Q1. And so my interquartile range, I'll just subtract those two values. So 21.1305 minus the answer, minus those two things. So that's equal to 5.261. That's my interquartile range. And so to find what my outliers are, I'll just plug them into that formula right up there. And so, well, on the high side, anything greater than 21.1305, plus, and then 1.5 times that, 1.5 times 5.261. So let's see what that is. So times 1.5, and then plus 21.1305. And so I get anything that is greater than 29.02. 29.02. So I don't think I made a mistake there. No, that's good. And then similarly, so anything greater than that's an outlier, or anything less than my Q1, 15.8695 minus 1.5 times 5.261. And if you do that, I believe you would get 7.98 approximately. So anything less than approximately 7.98. And so that would be, in essence, an outlier on the low side. So that would in essence be an outlier on the low side. And another little quick thing you could do is you could realize this is in regards to an outlier, it means that the center area is going to be, or in regards to the interquartile range, it means the center area is going to be 50%. So the center area is going to be 50% like that. And so what you could do is you could do inverse norm with, if you have this option on your calculator, a 0.5 and use the center area. 0.5 and use the center area. And it'll give you, in essence, the interval that contains the middle 50%. And so it gives you that interval, and so that's just a quick way to get your Q3 and your Q1. Okay, that's it. And thank you for paying attention, and I wish you much luck in regards to normal curve calculations.